Now we're going to take a look at how to tune control valves so that we can maintain a process at a desired set point. A control loop has two main components to it. The one is the item that we're controlling. In this case, we're going to be looking at a control valve and the controller itself. Our control valve regulates the flow of a liquid or perhaps a gas. Let's say, for instance, we're adding steam to a process to control the temperature. So to increase the steam flow rate, we would open the valve. To decrease the steam flow rate, we would close the valve. Our process, we need to make a measurement so that we know whether or not we need more steam or less steam. And so let's say, for instance, we're measuring the temperature of our process. So I have a thermocouple or some other similar device that measures the temperature of my process. And so I measure the temperature, and with it I want to open and close the control valve depending on whether or not I get my desired result. To do that, I have to have a set point in mind. So let's say, for instance, I want to control my temperature to 100 degrees Celsius. So that would be my set point, would be 100 degrees C. Now, if I measure the temperature of my process and I look at the temperature measurement, let's say it's 90 degrees Celsius. Well, that would tell me to increase my control valve opening to allow more steam to flow. Conversely, if my temperature is, say, 110 degrees C, I want to decrease that valve so that I can achieve my set point. And we do this by changing the output signal. And that signal goes to the control valve, and it determines whether or not the valve is going to be 100% open, 100% closed, or somewhere in between. Output signals can take various different forms. They can be an electrical current. In ChemCAD, which we'll be using, we have a current-based output, and that will take a small, weak electrical signal. In this one case, it would vary the current amperage between 4 milliamps and 20 milliamps. Other controllers, the output might be pressure, and it will change the pressure of air going to a control valve, and that air pressure actually determines what position the valve should be. So if we are using a output signal that's in current, the signal at 4 milliamps would tell it that the valve is all the way closed. At 20 milliamps, our valve would be 100% open. And at, say, 12 milliamps, which is halfway between 4 and 20, that would mean our valve is open at 50%. And this would be linearly interpolated between 4 and 20, so we can get a full range of valve openings. So the way the process will work is we measure the temperature, we compare it to a set point. If the temperature is too high, I'm going to decrease my output signal so that the valve will close. If the temperature is too low, I'm going to increase the output signal, which will open the valve. And if our measurement and set point are in 100% agreement, I'm going to keep that output signal constant. And this is how we're going to go ahead and start learning how to tune valves. So we'll be looking at that in just a moment. The general form of that output signal looks at three different parameters. And we'll go through this equation step by step. The output signal in this case is equal to a coefficient K sub P, which is known as the controller gain. And this gain will be multiplying everything inside the brackets. One term that it will look at is the error. The error is the difference between my set point and my process variable. Now, under some circumstances, we want the error to be the set point minus the process variable, or in other cases, it would be the process variable minus the set point. In either case, what it does is it looks at that error, and then if the error is positive, it will open the valve, and the error is negative, it will close the valve. So for instance, if we're heating a process with steam and our temperature is too low, we want to open the valve. So we would choose the error term to be the set point minus the process variable. This way, if the present value is too low, below the set point, the error will be positive and my valve would open. If we were actually doing a cooling loop where my temperature is too high, I want to increase the valve, or if my temperature is too low, I want to decrease the valve, I would actually choose the second term as my error. So if my temperature is too high, so that my process variable is greater than the set point, I want to increase the cooling water flow rate to the valve. So you have to pay attention as to how you define the error. In every case, the error will, if it's positive, we're going to increase the valve opening. If it's negative, we'll decrease the valve opening. Now we have a second term, which is an integration term. And in it, we have this term called TI, which is an integration time constant, or integral time constant. And we multiply it by the integral of the error as a function of time from time 0 to time t. And this term takes into account a phenomenon which we call offset. If we just work with a error term and nothing else, no integration or no derivative, then many times we'll find that we will have what's called an offset. Even though our temperature is not at the set point, it will just remain there. So we introduce this second term, which is an integral time constant. And then we have a third term, which looks at the derivative. And all three of these combined, the error, the integral, and the derivative, we multiply them by the controller gain. And we have a fourth term called the bias. And this bias is, no matter what the error is, the bias will be a constant number. The best way of thinking of it would be like if you're driving a car and you're holding this, you want to hold the speed, say, at 100 kilometers per hour. And so your foot is on the accelerator, which is attached to a device that regulates the flow of fuel into the car's engine. And if you're at the proper speed, say the 100 kilometers per hour, you're holding your foot at an exact position. Your error is 0 because it's the difference between your set point and your actual. But your foot is on the accelerator, so it's providing some fuel flow to the engine. If your speed is below 100 kilometers per hour, you want to increase the fuel flow. And so your error term, if it's below 100 kilometers per hour, if that's positive, you'll add a little more output to the controller. The controller will add more output, and that will increase the fuel flow. If your speed is below your desired point, or above the set point, you would decrease the fuel flow. So this bias term actually is just, if everything is at steady state, you want to have a constant flow going into your process. Sometimes, instead of working with a controller gain, we work with a term that's called a proportional band. proportional band was used back in the 1970s and 80s, but you'll still find some control systems that work with that. And it's just the reciprocal of the process gain, and the proportional band is 100 divided by the process gain. So instead of working with gain, our output is this term multiplied by everything else that we had before. Okay, but now we have to figure out what determines how large Kp should be, and what should be the values of the integral time constant and the derivative time constant. For instance, if our controller gain is too large, when you have even a small error, you're going to increase the output to that valve such that it will open up quite large, and then you may find that you do not achieve your desired set point but go above it. And the same would be true if we were above our set point, we would decrease the control valve position too much. And so what we want to do is look at what is the optimal value of the controller gain, what's the optimal value of the integral time constant and the derivative time constant. So we're going to use a process called closed loop determination of PID settings, and that's proportional, integral, and derivative settings. And this technique is we're going to use is called Ziegler-Nichols closed loop process. So again, we have our controller output, and it's going to be a function of the gain, integral time constant, and derivative time constant plus a bias. And this is how we're going to work it. We're going to first set our gain to be 0. So our output, when we look at it, it will be just the bias. Even though our set point and our process variable may not be at the right point. Our temperature might be too high or temperature might be too low. At this point, we're going to slowly increase our gain until we start seeing the controller take some action. With the gain being 0, the controller only has one output, and that's the bias. But as we take larger and larger values of our gain, we can then see the output changing. And what we're looking for is, when does the system become unstable? And what we're doing is we're searching for the point where it's no longer holding things constant, but actually beginning to oscillate. If we get to the point where our gain is less than what we call an ultimate gain, we'll find that our process will oscillate above our set point back and forth, but eventually it will dampen out to a stable value. Then we'll increase our gain some more. And what we're going to do is try to find the proper gain such that we get a uniform oscillation above and below the set point. At this point, the system is marginally unstable. If we increase the gain further from that point, where we're above what we call the ultimate gain, then we'll start seeing oscillations that are actually increasing with time, and things can get very, very uncontrolled. So we're trying to avoid this scenario altogether. And what we're looking for is this point here, where we have some stable oscillations that do not increase or decrease with time. Once we find this ultimate gain, we can then properly set values for our gain, our integral time constant, and derivative time constant that will give us stable oscillations. So let's say we keep increasing our gain until we find that we're at that stable oscillation. And then once we're there, we're going to look at the time difference between oscillatory peaks. So this time difference is what we call the ultimate period, the time between one peak and another. So if I find my ultimate gain and the period associated with this ultimate gain, I can now calculate what are my proper values. Now you have various different control systems. Sometimes you want proportional only control, which we call P control. In that case, all we have is a gain, and we don't have an integral or derivative time constant. If we have that case, then the proper value of our gain would be 0.5 times that ultimate gain. If we have proportional integral control, or PI, the proper value of our gain, K sub P, should be 0.45 times that ultimate gain. And our integral time constant will be that ultimate period divided by 1.2. And our derivative time constant remains at 0. If I chose PID type control, proportional integral and derivative, I want my gain to be set at 0.6 times the ultimate gain, my integral time constant at 0.5 times the ultimate period, and my derivative time constant at 0.125 times the ultimate period. And this will give us the proper values for controlling our process.
Let's take a look at a simple process. And here we're going to be preparing an ethanol water mixture by blending together pure water and pure ethanol in the right proportions. And we're going to try to get the desired composition in terms of ethanol mass fraction and also the total flow rate that we desire. Our process starts off, we have a water feed that's controlled by a control valve. And in line, we're connected to a level controller. This level controller will look at a feed tank where we're going to be storing our water in. And so what we desire to do is use the level controller to keep the level inside this feed tank to the proper value. Coming out of the bottom of my feed tank, I have a pump system with a control valve. We have a length of piping followed by a pump, another length of piping, a control valve, more piping, and then this stream will enter a mixing tank. I have a similar thing on my ethanol side. I have pure ethanol feed. It's feeding a supply tank using a control valve and level controller to keep the level inside my ethanol tank to the proper value. Again, out of the bottom of my ethanol tank, we have piping, a control valve, and a pump. And then these also get sent to a blending tank where the ethanol and water are mixed together. And then they leave the tank. And what we're trying to do is keep the flow rate and composition at a particular value. This tank is going to operate like a CSTR with an overflow. So we'll find that the level inside the tank will be constant. The other two tanks, the feed tanks, they're not going to be constant, or they can change because we have feed going in and material leaving. And if our feed is coming in at a larger rate than what we're pulling out, then the level will increase. And conversely, if the feed is less than what's coming out, the level will decrease. So our vessel is a vertical tank. It has a diameter of 4 meters and a height of 6 meters. And it's at atmospheric pressure. And initially we have water in this tank, and that will be at this current level. Our outlet flow is a volumetric flow rate, and we're going to control that with the pump and control valve downstream of that. And so that we'll be able to draw out liquid out of the tank, and that will supply the water to our process. Initially in the tank, we have pure water, about 31,000 kilograms of pure water, and the temperature is 26.8 degrees Celsius in 1 atmosphere. I have the same tank for my ethanol, same dimensions, same or similar initial liquid level, fixed pressure. We have outlet flow on that as well. But in this case, our charge is now pure ethanol in that tank rather than pure water. The control valves are already pre-selected in terms of what the control valve coefficient is. And we're going to use a linear valve for the feed valve going into our tank. And in this case, we're going to fix the valve position and adjust the flow rate. Our current valve position is at 50%, and this is actually selected by the level controller that's just downstream. One other thing that we have to be aware of is what we call valve time constant. In this case, 0.2 minutes. And the reason why we have a valve time constant is a valve opens and closes in a finite amount of time, and this time constant will allow us to reflect that. So if we want the valve to go from 0 to 100%, that time constant will take about 0.2 minutes or 12 seconds to happen. I have a similar valve for my ethanol. Same valve coefficient C sub V. Again, it's a linear valve as well. It's being controlled by a level controller, given this ID, which is 17. And it also has a similar valve time constant. Let's look at the level controller. And this is how it works. We have a set point that we want to maintain the level at. In this case, I want that set point to be at 4 meters. Okay, I tell it that the minimum and maximum for my tank, in this case, the minimum value of the level will be 0.01 meters, and the maximum value it can be is the full height of that tank, which is 6 meters. Our controller input is 4 milliamps as the minimum, 20 milliamps as the maximum. My bias, or my steady state output, I set at 12 milliamps. That's equivalent to a value of 50% opening, because 4 milliamps is 0% open, 20 milliamps is 100% open, 12 milliamps is exactly midway between. And recall, when we want to tune our valve, we want to set our gain to be 0 so that we can determine what that ultimate gain would be. Well, proportional band is equal to 100 divided by that gain. Well, 100 divided by 0 is infinity. So my proportional band, I can't write in infinity in this box. So I'm going to set it at a very large number, 10,000. We can even go to 100,000. I tell it that the controller is controlling valve number 1. Okay, the variable it's going to control, it's going to look at equipment number 3, and equipment number 3, we're going to look at the calculated level for liquid number 1. Since we don't have two separate liquid phases, we're only looking at one liquid level, so we're going to use liquid level 1. And the units of that variable are in terms of length. And if you look in the units of measurement, length is measured in meters. And we would click OK. So this controller is going to open and close this valve depending on what that level is in this tank. And what we're going to do with the controller is try to find the ultimate period where we have stable oscillations. And we're going to do that by changing the proportional band. But we want to be able to measure certain things. Okay, so I'm going to control this valve, but what I'm looking at is level. So I want to find out at what point does the level start to oscillate up and down so that we can determine what that ultimate period is, and also the ultimate proportional band. So I have to record things that will allow me to see this. Under the Run menu, you'll see that we have a menu item that allows us to select steady state or dynamics. This is a dynamics course, so we're going to look at things that are not steady state, so we check dynamics. Under the Run dynamics, we have a menu where we can set the run time. We can look at recording streams and unit ops. So I'm going to look at record streams. So at the present time, I'm only recording stream number 35, and I'll click OK. And 35, if we look all the way out, 35 is my final ethanol water mixture. So with that stream, I want to look at the total flow rate and the ethanol composition. But I'm controlling a level inside my tank. I'm not interested in that stream. I'm actually interested in the level of this tank and the position of this valve. But I go back to my Run menu, hit Run Dynamics, and look at Record Unit Ops. Okay, so I've selected various different IDs. My control valve is number 1. Okay, and I'm going to check the box that says Runtime Plot. This will allow me to see what's going on with that valve when I run this program. Also, I'm going to plot unit op number 3, which is my tank. I'm going to plot that as well. And I'm going to do the same for other control valves and my other tanks as well, so that I can use that information to tune my valve. So I'll click OK. For equipment ID number 1 is my valve, I'm going to take a look at the valve position as a function at a time. And this will give me a chance to see how much that valve is moving, whether it's increasing or decreasing, depending on how I like it. Click OK. For my tank, I'm going to look at the level number 1. Okay, in this case, equipment ID number 3 is the tank. Calculated level 1 is the variable I want to look at, and click OK. So when we run our program, we're going to be graphing the valve position and also the level inside that water feed tank. We look at our Run menu under Dynamics. I'm going to click on Set Runtime and hit step number 1. So at the present time, I can run for a total of 2,000 minutes. And this is in terms of simulated minutes, not actual minutes. And I'm going to take a small step size to do the integration and click OK. Also, on the Run menu, I'm going to look at my convergence parameters. And I want to check the box that says Allow Dynamic Editing at any time. This will allow me to stop my process, make a change, and start my process right at that point. And by default, this box is usually not checked. So you want to make sure that that's checked as well. So when I look at my level controller, right now, I have a set point at 4 meters. My steady state output is 12 milliamps, which is the same as 50% valve opening, and I got a large proportional band. When that proportional band's large, means my gain is very small. So when I look at my controller output, it's going to be primarily only the bias, which is that 12 milliamps. So let's take a look at what happens when I click the Run menu, Dynamics, and Run from Initial State. So here we're looking at two plots. Okay, I'm going to pause it right now. I'm going to hit the Escape key on my keyboard, and that will pause the program. Okay, so at the value of time, we find that the valve position really isn't changing much. It's only about 50% because I don't have a large gain in my process. And if I look at the height in my tank, it's at 2.48, a little bit above that, and it's decreasing with time. So essentially, what I have is my valve is not open far enough to maintain that constant value. So now I'm going to do is allow my controller to do some work for me. So if I double click on my controller, okay, we're going to increase the gain, which means I'm going to decrease my proportional band. So let's see what happens when I go from 100,000 to say a value of 10. And I'll click OK. Now remember, what we're looking for is a stable oscillation of the height in my tank versus time. So now I want to click on the Run, Dynamics, and then hit Run from Current State. So what do we see? Our valve is starting to open, and actually we're at 100% opening, and my level is still decreasing. Okay, so that means I'm drawing out much more liquid than I can supply. And so we find ourselves in the case where I can't control my level. I'm going to pause and let's take a look at why that's happening. Okay, so I'm going to look at my process. Even though my feed is coming in at its maximum value, I'm at 100% opening. I can't supply enough to go into my tank. It's being drawn out too much. So when we look at a control valve, we look at the maximum flow that can come in will be proportional to the maximum valve coefficient. So I selected a valve coefficient of 12. It looks to me that it might be too much or too small to allow the flow rate I want. So I'm going to change this and just double that valve coefficient and see how well this will work. So now I'm going to be able to double the flow rate into my tank more or less, and we'll see what will happen. So I'm going to go under Run, Run Dynamics, and click Run from Current State. Okay, what do I see happening? Now my tank is starting to fill up. I'm at 100% valve opening, and this will run for a period of time until I reach my target set point of 4 meters. Now, I don't have to have it at 4 meters. That was an arbitrary level. So I can change that value to something where I don't have to wait forever for it to reach that point. So I'll hit escape, click OK, and you can tell that I'm about 2.62 meters in height. So I can make that my set point. So instead of 4, I'll put in 2.62. So right now I'm slightly above my set point. Click OK. Hit run. Run dynamics, run from current state. Look what happens to my valve. The valve starts to close. Now it's at about 50% opening, and my level is now starting to go down. Remember, I wanted my level to be 2.62 meters, and we'll see what happens as we approach that we should be able to hold that value. Okay. Really what I want to do is find out when I start to oscillate. So I'm going to pause and look at my PID controller here. So I am not yet at a point where I see the stable oscillations. So I want to go to a higher gain, which means a smaller proportional band. I'm going to set my proportional band equal to 5 and then hit run dynamics from the current state and see what happens. Do we reach oscillations or do we just continue to see a smooth change here? Again, not seeing that oscillation, so I'm going to pause, click OK. Instead of 5, let's make it 1. Run dynamics. Okay, so now what do we see here? Um, Started to rise and now it's coming back down. And we're approaching that 2.62 meters in my tank. But I don't believe I'm actually in a point where I'm in an oscillation mode, but we're seeing a little bit of a change in course here. So it's beginning to fluctuate up and down. And this might be at a point where it doesn't change with time too much. Going to let it go a couple more cycles and show you how to look at the entire picture. So I'm going to hit escape and under my plot menu, I'm going to go down to dynamic plot and I'm going to look at dynamic unit op history. Need to click on my tank because that's the one I have the history on. So plot, dynamic plot, unit op history. I'm going to look at my level with respect to time. I'll click OK. And so you can see from time 0 how the level was decreasing. And here we want to focus in on whether or not we're oscillating. So I'm going to click on this region and see what my values might be. And I can't get it to show too much of that. So I'm going to look at my valve position instead. This might tell me more. So I'm going to click on the valve, plot, dynamic plot, unit op history, and valve position. And we can see that we have just some semblance of oscillations, but it's hard to tell whether or not it's significant. So at this point, what I'm going to do is let's try a little bit smaller proportional band. I'll go 0.5 and click on run dynamics, run from current state, and see what's going on with this now. Okay, see if I get that oscillation period to happen again. And so we're starting to see some semblance of oscillation. That looks pretty regular. And I'll hit escape and click OK. All right, so here we find that we have a oscillation going on, and we'll call that pretty stable. And so I have my proper gain set that will give me that oscillation. Now I need to know what is the period. Well, we want to know what's the period between peaks or the period between the trough and the peak, and then I double it. So I have about 87.58 at a trough and 90.28 at a peak. So the difference is approximately, we'll say about 3 minutes in between the bottom and the top. So my ultimate period, we'll say, is 6 minutes. And my ultimate proportional band is at 0.5. So I'll click OK. Now we want to do is look at our table to determine what's the proper value for my uh, ultimate proportional band and my ultimate period, so that I can get that into the proper proportional band and integral and time constant. So we're going to need to do some calculations to do that.
So from that exercise, we found that the ultimate proportional band was about 0.5, and my ultimate period was 5.8 minutes. The calculated value of the ultimate gain would be the equivalent of 100 divided by 0.5, which is 200. And if we look at our chart, Kp, if I use a PID controller, should be zero point 0.6 times Ku. So we would find that a value of K sub P would be 120. And recalculating proportional band, it will be 100 over Kp, or 0.83. For our integral time constant, it should be 0.5 times the ultimate period. Our ultimate period of 5.8 minutes, so 0.5 would be 2.9. And for our derivative, it's 0.125 times our ultimate period, and that calculates to be 0.725.
Let's now enter those values into our ChemCAD results. So for my true value proportional band, we'll use 0.83, integral time constant 2.9 minutes, and derivative time constant of 0.725, and click OK. Now to test our theory, what we want to do is click on run from current state, and see how well our process responds. Now it may take a couple of cycles for it to line itself out. But what we want to watch is our valve changing by a significant amount? And is our level being adequately controlled at 2.62 meters? And so as we're going on here, we're seeing that it's cycling 2.62016 and going down to, just below 2.62. So our level is being controlled quite well. But a true test of a controller is whether or not it can handle an upset or a change to my process. So I'm going to hit escape and I'm going to look at changing my process. And I'm going to do that by looking at my water feed pressure. Right now it's at 2 atmospheres. And so let's say my water pressure should start to fall. I'm going to make that at 1.5 atmospheres. Now, if you recall with a control valve, the flow through the valve is proportional to the square root of the pressure difference in the valve. And so if we have a decrease in upstream pressure, we'll find that our flow will change. So if we have a well-tuned valve, it should be able to control that uh, to the level of 2.62 meters. So going to go to the run menu and run from current state. So our pressure decreased, so our valve has to increase, and we find that we drift down to 2.145. Now it's coming back up. And so we'll see whether or not we'll be able to handle that pressure uh, decrease and see if the valve is actually performing well. So even though we had that significant pressure loss, we'll find that we're still be able to maintain that level right at our desired point of 2.62 meters. And so we would be in proper tuning for this, and this will allow us to be able to control our process even though I might have some upsets. So I'll pause that. So I now have a process where I tuned my water feed valve. Okay, and what I'm going to do next is this. Under the run menu, I'm going to go to the dynamics and I'm going to save this as the initial state. Even though it says you're going to lose the original, that's fine. So right now, at time 0, I have a process that will allow me to continue on to make some other changes as well. And for the assignment, we have 4 valves that we want to tune. I have an ethanol feed valve. I need to tune that in a similar way that I tune my water feed valve based on its level controller. Okay, so if we look at it, I have the set point equal to 4. I'm going to click OK. And if I look at my initial liquid level, it's at 2.187 meters. So I'm going to sort of make this a little easier for us all, is we'll make this at 2.7 meters for right now. Now remember, this is just a feed tank. As long as we don't run dry or overflow the feed tank, that's the only purpose it has. The level can um, be at a low value in the tank or high value in the tank. So what you want to do is use that same Ziegler-Nichols technique to adjust the proportional band integral time constant or calculate the integral time constant and the derivative time constant by changing my proportional band, start off at a high value and make it smaller until we see the oscillations begin to decrease. Now remember, right now the graphs that we were looking at were the water feed valve and the level in the water feed tank. Okay, I'm going to uncheck these boxes. So now what we want to do is look at the level in the ethanol tank and the valve position for the ethanol feed valve. So under my run menu, I'm going to hit run dynamics and I'm going to look at record unit ops. So I don't need to look at my water feed tank. So I'm interested in control valve number 6, which is my ethanol feed. And I'm interested in my tank of ethanol, which is number 16, and click OK. So when I run this, I have to tell it, okay, equipment number 6 is my control valve for ethanol. So I want to look at its valve position. Type in and click OK. And for equipment number 16, which is my ethanol feed tank, I want to look at calculated level 1. And I can type in as my plot title and begin to find out what's the proper tuning values for the level controller. Now, like the water, you may find that the ethanol feed valve might be too small, and so you would have to look at increasing that valve size, and you do that simply by double clicking on it and change the valve coefficient and click OK. Now we're going to do two other controllers that we're going to tune. I have two other valves in my process. I have a water valve that's feeding my mix tank, and I have an ethanol valve that's feeding my mix tank, where they're being blended together. And so what we're going to do is control the composition of our ethanol in our tank, and we're going to control the total flow leaving my tank. So coming out of the bottom, I have a composition controller. And at the present time, I'm looking at the mass fraction, component mass fraction of ethanol. Okay, mass fraction has no units, so I use internal units. And I'm looking at stream number 35, which is the outlet stream. So I'm going to control that composition. Say right now my set point is 0.4. Okay, and I'm going to be controlling my ethanol valve, which is number 21 on my screen. So that control valve is number 21. Now for mass fraction of ethanol, that has a minimum of essentially 0 or 0.01 and a maximum of 1. So now we have to set our sensor equation so it has a maximum value of 1 and a minimum value of something very close to 0. So that controller will activate on that valve. If I double click on the valve, it is a specified valve curve. If you remember looking at the Mason-Nealon catalog, they give us a valve coefficient as a function of valve position. We'll see what that will look like in just a second. Okay, I'm telling it that controller number 31 is controlling this valve, and at the present time I have a time constant for that valve of 0.3 minutes. And I'll click OK. And I'm specifying the valve curve. So if we look at different values of position, this is the different percentages of that full coefficient. So this valve curve is that of an equal percentage valve. And I'm going to control the total flow by adjusting my water flow rate. The control valve is number 10. If I look at my control valve number 10, that controls the water flow to my mixed tank. Okay. At the present time, I have it set at 20. Okay. And that 20 is looking at stream number 35, which is the outlet stream. And what I'm looking at is the actual volumetric flow rate, and the units are liquid volumetric flow rate. If you look at the unit selection in the ChemCAD, it's going to be in gallons per minute. So again, we're going to look at controlling the flow rate of water to give me a total flow rate that's leaving. And we're going to control the ethanol flow rate to give me the composition. So these two valves are going to have to work together and be controlled well in order to achieve my given target. So what we want to do is find out a way of controlling the composition that I want. At the present time, my composition, looking at a weight fraction, right now it's at 0.436 for ethanol. Okay, so what we want to do is tune that valve to give me a constant value. And then when we're done with that, we're going to tune the water flow rate valve using the flow controller to give me the target value. So we should be able to get perhaps up to about 95 gallons per minute might be the max. But that would mean that my water flow rate and my ethanol flow rate, those valves might be at 100% opening. So my composition can't be as high as 1. But we want to look at maybe lower flow rates, say at instead of 100 gallons per minute, maybe look at a 50 gallon per minute. And I should have a wider range of controlled values for my ethanol mass fraction. So what you're going to do, and this will complete your studies for process control, is you're going to first tune the ethanol feed valve using the level controller. Then we're going to control the mass fraction of ethanol using that mass fraction controller and the ethanol feed valve. And then finally, control the total flow with this valve here. And so this will allow you to be able to learn how to control valves in the field and give you practical exposure to process control that you can use in your jobs.